Hello guys, welcome back. We're gonna talk about psychometric chart. I'll give a brief explanation, history, and how it's built so you understand better the use of this psychometric chart. So let's start with a brief history. It was created by William Carrier around 1904, and it was based on several works, previous works, mainly by saturation tables by Professor Marvin, but data went back up to Newton. So he developed this chart in order to make quicker calculations. Recall that at that time we don't have computers or electronic calculators, so even it was made all by hand calculations, aided by sliding rule, if you were lucky, or logarithmic tables. The original one, and we're going to see the original one at the end of this presentation, didn't have as much information as the current one, so it has been improved over the years. You can find a brief history. It's a 5-page reading in this link. And just to remind you that a psychometric chart is a useful tool that relates all the main parameters carrying an AC calculation and also gives a visual representation. So we're going to start with our old PVT diagram. In this diagram, what we are going to see is we're going to start with our PVT diagram. This PVT diagram is for water. So and we are going to see it from this side. So our I, it's here. If we see it from P and T diagram, will look like this. So this line that we are looking for, which is the vaporization line, this line will be this line here. Okay, so on this side we have vapor, on this side we have liquid. So we are seeing from the this will be volume. Okay, so we know this, and we can put it in is. So we can create this plot, and to create this plot, the only thing that we did is we have a temperature. Let's say we have 25, and then we have PV as the saturation temperature at 25 degrees. We should call this better PG. So this will give me this number, right? Around 2.3. We're gonna have the right result. Okay, so this diagram is PV diagram. Now, we recall that our relative humidity or humidity ratio is 0.622, the vapor pressure, divided by P minus my vapor pressure. If I use PG, that means that I am in saturation, then my omega will be let's have a quick analysis of this part. Let me just finish this. Atmospheric pressure will be constant or fairly constant. This is also a constant. So this omega is just a function of PV or PG. So I can change this to be omega, right? If for every temperature that I compute PV and then I made this transformation, I will have omega. So let's see how does it look. And you can see that it looks exactly the same. This line will be, this line that we are seeing here is saturation, right? So everything on this side is vapor. As long as we heat, we have liquid. So we already know how to compute our data, and we see that this graph, it's T and absolute humidity or humidity ratio. So and this line corresponds actually to a relative humidity of 100. So let's say that we have one relative humidity. Let's just, for the argument, say that we have a relative humidity of 50%. And also that we have the pressure is 100 kilopascal, and let's have a temperature of 20 degrees. This will be a dry bulb temperature. Okay, since we know omega, relative humidity is PV divided by PG, and we already know PG. PG is the saturation pressure at 20 degrees. This is 2.23 kilopascal. And we know omega, we can solve for PV. This value will be, well, if we have PV, we can get also the humidity ratio, kilograms of dry air. So I said it was 20 degrees along this line, and it's 0.014, a little bit above this 0.12, so it should be around here. And the relative humidity constant line will be like this. So if I do the same and I change T, keeping equal at 50%, and then I keep the changes, keeping this 75%, and T changes, keeping this at 25%, I'll have a graph similar to this. And I can see constant relative humidity lines. And all I did is change temperature 1, fix my relative humidity, and compute the absolute humidity for each point, and then I join them together. Okay, so that's the first line. Now we recall that we have an expression for enthalpy, and enthalpy was Cp times the temperature plus omega times Ag. And let's say that we have a temperature of 20 degrees and an enthalpy value of 59.39, pressure still 100 kilopascal. So if we know T, we can get Ag to be kilojoules per kilogram. This is Ag at 20 degrees. If we have all this, my only unknown is omega. So omega will be, if I substitute, it will be around here. I can do the same as I did before. I keep H at 59.39, and I change temperature between two values. And for each of these values, I compute omega, and then I will graph it. I can do the same for H at 100.6 kilojoules per kilogram, and again change temperature between two values, and using this same procedure compute omega. And if I do it, I can plot You can see these two lines are the lines that I am getting, okay? So I can do this for number of enthalpies. Next, we're gonna do the same for TV. We remember that we have a wet bulb temperature, and for that, we remember that we should have TDB and T wet bulb. So if I have a combination of these two, just like we did in the problem, we will compute omega 2 to be, okay? Once that we have omega 2, we can get omega 1. So we can, if we know these two properties, we can compute these two temperatures. We can compute each of these properties just like we did in a previous video. So for each TdB, and compute omega, and then we repeat. Keep 35 degrees and compute omega when we change TdB. If we do this, for instance, for this first value, we're going to find out that omega is 0.009, 50 degrees and 20. If we repeat it several times, we're not going to have now these lines. Okay, so now we have absolute saturation, relative humidity, saturation, relative humidity, enthalpy, wet bulb. We're missing one, which is the volume. So now we are going to have to compute volume. So let's say that we have a relative humidity at 50%, and again pressure is 100 kilopascal, and for a temperature of 20 degrees, we already know that we are talking about this point. We can compute our PV. Now that's PV, that's the partial pressure of vapor. We can do partial pressure of air to be the atmospheric pressure minus PV, and this the volume of air will be defined as the gas constant for air, temperature of the mixture by partial pressure of air. And this temperature of mixture will be the 20 degrees plus 273 to express it in Kelvin. If we substitute, we're going to have a value of 0.805. So we can do the same several times and get a constant volume line. It will be these two, okay? So now we understand how our psychrometric chart is built. A simplified version that you have in your book. You can see the relative humidity, constant enthalpy, constant well bulb, and constant volume. Okay? Please notice that at saturation, the dry bulb, the wet bulb, and the dew point are the same. That's characteristic for this point, for any saturation point. Okay, so we mentioned that we are going to see this is our first, this is the original Williams-Carrier chart. So you can see that they have the relative humidity, they have the humidity ratio, and the temperatures, but they didn't have the enthalpies. So over the years, we added, we have the humidity ratio, we have enthalpies, we have dry bulb, we have relative humidity, and we have constant volume and wet bulb. Okay, we can do the same in ease. And we can draw our line, and again we have the saturation line, a constant volume, constant wet bulb, temperature, humidity ratio, dry bulb. We are not plotting the enthalpies. Okay, this is very handy because now we can define any process as in a very visual way. Cooling without dehumidification will go in the direction of reducing the dry bulb temperature. We are adding heat without humidifying. It's a constant humidity ratio. We are going in the direction of increasing the dry bulb temperature. So this will be a resistor, for instance. This could be a refrigeration system. Okay, if we are humidifying, let's say that we are adding water, just go in the direction of increasing humidity ratio. If we're dehumidifying without changing temperature, let's say with silica, we go in the direction of decreasing the humidity ratio. We can be cooling and dehumidifying by using, again, a refrigeration system, or heating and humidifying by adding vapor or steam. Okay,